So I will present a physics-focused experiment that was done through our cloud interface on the Sycamore chip. And here in this experiment, we're focusing on something that we call quantum circuit kinetics. And before going further, I would like to say that this has been a Google AI quantum team effort. Nonetheless, I'd like to highlight the contributions from Xiaomi to the experiment, Igor Aliner for help with theory, and our NASA collaborators. Our motivation is basically to do the most natural task for our NISQ device, which is circuit kinetics. And I'll give in this talk an example of that. What we're doing is we're characterizing emergence of ergodicity from an initial product state using local observables familiar to physicists. To interpret the results, we will need to model noisy Sycamore circuits, and using that model, we'll be able to distinguish operator spreading from effects of noise. And then I will show how all of this works in data. And let's start with a very simple circuit shown here. Assume we have a lot of qubits and apply some unitary U. And then immediately after that, U dagger. Obviously, this is identity. But the situation becomes much more interesting if we apply a local operator to one of the qubits, which we call a butterfly operator. Right? If this circuit U is sufficiently long and is random, all conjugated operator of butterfly U and U dagger itself approaches a random unitary up to some small number of constraints. And therefore, it will be described by some version of random unitary ensemble. We are interested here in how that happens, actually. How does this butterfly operator, which was local, becomes a matrix spread over all the Hilbert space. Right? And we, as a physicist, we want to think of this as using a local probe. So we apply a measure operator at some location different from the butterfly operator. To visualize how this dynamics proceeds at these intermediate times, we can think of the butterfly operator, which can be, for example, a Pauli Z operator, as conjugated by U and U dagger, and we can expand that into the Pauli strings and multi-qubit Pauli strings. And the dynamics of these coefficients here will describe the dynamics of the operator. And a good visualization of this is shown here. So assume at the moment where we apply the butterfly operator, we have this operator looks like identities, which are shown here as empty circles on each qubit, and the sigma z operator applied to the butterfly qubit. Now, as we apply a unitary U and U dagger, this butterfly operator gets mapped onto a superposition of Pauli strings of 2 qubits, and then 3 qubits and 4 qubits as the circuit becomes larger and larger. And this dynamics can be captured actually with the local measurement, applying an operator such as sigma z1 at a different location. And in particular tool for that is the known as out-of-time ordered correlator. And I don't have time to go into detail, but to give you a flavor what we expect from this operator, let's look at its dependence on the function of time. In this situation. At the very short times, this butterfly operator commutes with the measure operator, and therefore, in this expression here, we can switch the places between the two. And what we will get is square of Pauli matrices with square to identity. And therefore, out-of-time order correlator will be simply 1 at short times. In the opposite limit, we know that, as I said before, this butterfly operator conjugated by U and U dagger becomes a random matrix, and therefore we expect this correlator to be exponentially small. And in between, we have this interesting kinetics that we want to study. That is a small, smooth front as shown here, typically. So we can study this on a 16-qubit chain, where we choose site 1 as the measure operator, and we will place butterfly at different locations. And the circuit we choose is natural for our Sycamore chips, consists of single and 2-qubit gates, where 2-qubit entangling gate is square root I swap for this particular experiment. And we use a single qubit gates, which are pi over 2 rotations with respect to the axis in the equatorial plane chosen at random. So in this way, we generate an ensemble of circuits. And in the following, I will talk about ensemble averages and individual circuits both. And this is an example of simulation of this out-of-time order correlator. for different locations of butterfly. To make it easier to follow, I'll label the colors of the location of the butterfly in accordance with the lines on this plot. So for example, for this blue location of the butterfly, auto decays really fast. In the opposite limit, this magenta colored butterfly located at site 16 corresponds to this magenta line here, which shows the behavior. Basically, auto stays at 1 for a long time, which takes a sufficient amount of steps to propagate for the operator from one side to the other. So this is what we expect from numerical simulations. What we see in experiment is shown on the right, and the figures are quite different. And the reason, of course, is that in the hardware experiment, we have errors, and we need to interpret this data, we really need to account for this error in a careful way, effect of error on the actual signal. And therefore, we need a theoretical approach for that. And for average out-of-time order correlations for random circuits, actually, it is possible to develop a detailed theoretical approach in presence of noise. And the intuitive reason for that is if we average over circuits, that eliminates quantum phases. As a result of that, dynamics of auto for a quantum circuit can be mapped onto a Markovian population dynamics in a space of operators, Pauli strings. And this mapping can be done for a deterministic 2-qubit gate we actually use on the device and in presence of noise. And what this population dynamics will predict is the average shape of the auto as a function of time. And this population dynamics doesn't have the sign problem and therefore is efficiently simulable. We can use it to predict the fidelity of the auto circuits and the output of the experiment. And in particular, we start to assess the fidelity starting from this simple circuit, which is supposed to give you an identity and therefore is a really good reference circuit. We can describe noise by Krauss operators. However, again, averaging over circuits eliminates single qubit phases and therefore is sufficient to have a single parameter, a symmetrized local Pauli error to describe the fidelity. And we can connect the fidelity of the circuit to the statistics we calculate in population dynamics and one parameter. And just take this theory and compare it to the data on this, what we call an echo fidelity experiment shown in blue here. What we do is we take this population dynamics and use this one parameter to fit the data, which is shown in red. The fit and extracted Pauli error is about 1.14%, which is consistent with what we measure for individual pairs of qubits. And therefore, this verifies our experiment. And now we can go in further and use our knowledge of the fidelity from this reference circuit to make the data closer to the experiment. So this is what we had in simulation. And now what we do is we normalize the auto by this fidelity of the echo circuit. And the resulting behavior turns out to be very similar to the ideal circuit. And actually this ratio also, again, fidelity of echo signal cannot be coming from entanglement. It can only be coming from noise. And therefore the difference between auto and echo signal distinguishes the ergodicity in the circuit from the noise. And this match between theory and experiment notice was obtained for a rather large circuit, which is comparable to what was done in a quantum supremacy circuit. And this is an ergodic circuit, right? So it's very sensitive to errors. Now, a similar procedure can be done now for individual circuits. And here, auto really becomes a very interesting tool to investigate specific circuit kinetics, right, for individual circuit. This on the right show, I'm showing this normalized auto data typical for this. And what we see here is the structure is much more interesting. And what this behavior here is basically an analog of what is known as mesoscopic fluctuations in kinetics of metals. And auto is an excellent tool to study it. So again, to conclude, we detected emergence of ergodicity from an initial product state, and we were able to do verification with theory in presence of noise for the average case. And for individual circuits, a talk is a tool to study circuit kinetics. Thank you very much.